Hello everybody. Welcome to Chapter 2, our chapter on logic and reasoning. Now, logic is an important part of geometry because it's what allows us to come up with new properties, new formulas, or new theorems about geometric figures or geometric objects. Also, having a good logic foundation is going to help us solve more and more complicated problems as we move forward. Okay, so that's why we're focusing on logic for this chapter here. In section 2.1, we're going to talk about patterns and inductive reasoning. Our objective is to use inductive reasoning to make conjectures. All right, we'll explain what the heck that means as we go through the lesson here. So first things first, what is inductive reasoning? I'm going to say it's reasoning based on patterns you observe. Okay, so reasoning based on patterns. So let's take a look at a few different patterns here. Problem 1 says, what are the next two terms in each sequence? Okay, a sequence is just a list or a pattern. And then what we can do is we can figure out what that pattern is and use it to make some predictions. Okay, the first pattern we have, 3, 9, 23, 81. Basically here what's happening every time is we're multiplying by 3 to get from one number to the next. 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81. So if I want the next two terms, I'll multiply 81 by 3, which would give me a 243. And then we'll multiply that by 3 to end up with a 729. Okay, and then we could continue with that pattern, but yeah, we'll just do the next two terms. All right, part B, we've got another sequence. This time there's fractions involved. Okay, usually what you want to do to solve or find the pattern in fractions is look at the numerator and denominators separately. So the numerator, for example, goes 5, 10, 15, 20. Basically, we're just counting by fives. So the next term would have a 25 in the numerator, and the next one would have a 30. Okay, notice I figured that out without even looking at the denominator yet. Denominator, same thing. Let's look at its pattern, 3, 6, 9, 12. Looks like we're just counting by threes, so we could say 15, 18. All right, so again, with fractions, look for those patterns separately. Okay, in C, we can also have patterns with geometric figures. So here we have a circle with a triangle inside, 3 sides, then a square, 4 sides, then a pentagon, 5 sides. Okay, so let's draw one more term in this sequence here. Okay, I'm going to make a hexagon with 6 sides. Now you're not judged by your artistic abilities by any means. Okay, there we go. It doesn't look pretty, but it's a hexagon. We'll skip the heptagon. We'll say we're good for now. All right, so when we're looking at patterns, when we're using inductive reasoning and we're figuring out what those patterns are, we're making a conjecture. Okay, a conjecture is just a conclusion you reach using inductive reasoning. So basically we made conjectures about the patterns in the last problem. Okay, and we'll use that word conjecture as we move forward today. So problem 2, part A says, look at the circles. What conjecture can you make about the number of regions 20 diameters form? So what I have going on here is that in the first circle I have one diameter. Okay, a segment that goes from one side of the circle to the other through the center. So we can say D is equal to 1. And as far as how many regions I have, I count 1, 2 regions the circle split into. So I could say R is equal to 2. Second circle, I see 1, 2 diameters, so we could say D is equal to 2. And there are 1, 2, 3, 4 regions in the circle. We'll say R equals 4. Now what I could do is I could keep counting up like that, or I could draw a circle with actually 20 diameters in it. Now that's going to be a little bit of a pain to do. It's going to be probably a pretty ugly circle. So what I'd like to do is I'd like to look for a pattern, a relationship between the number of diameters and the regions, so I can make a prediction about the 20 diameters without actually drawing them. Okay, now it looks like what's happening is to go from my diameters to the regions. I'm multiplying the number of diameters by 2. 1 times 2 is 2. Okay, 2 times 2 gives me the 4. Now let's see if that pattern holds true for the 1, 2, 3 diameters. When D equals 3, we've got 1, 2, 3, 4, 5, 6 regions. Yep, so it looks like what I'll do is I'll go times 2 to get R equals 6. So what I can do then, I can make a conjecture. The regions is the diameter times 2. So when D is equal to 20, we'll just multiply that by 2 to end up with R equals 40. You would expect to see 40 regions for the 20 diameters. We can also make conjectures about repeating patterns, such as this one here, RWB, RWB, dot, 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 meaning that's going to continue, RWB, RWB, RWB. So problem 2 part B says, what conjecture can you make about the 22nd term in this repeating pattern? Now what I could do with a problem like this is just count out 22 terms in my pattern. Now that'll get less practical as my numbers go up here, but we could do it that way. What I can do instead is I can figure out what the pattern is. Now the thing to recognize with this one is that my length is 3. Okay, the length of the pattern is 3, meaning that every third term is going to be the end of my pattern. It's going to be a B. So as in the third term will be a B, the 6th would be a B, the 9th would be a B, the 12th would be a B. So what I can do with that is I can find a term that's close to the 22nd term and divisible by 3. So as in the 21st term, I know it will be a B. Okay, meaning that if I count up by 1 with my pattern, after B comes the R, we'll have an R for the 22nd term. Okay, so the idea here is use the length of the sequence to figure out something that's close to the term we want, okay, through division. And then once we have that, we can count up or count down to figure out what the actual one we're looking for is. All right, problem 2, part C is the same thing. Why don't you take a minute, pause the video, work through that, try it on your own, and then hit video or hit play to check the answer. In part C, we want to figure out what the 103rd term of the pattern 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 is. Now again, the trick is I can figure out what the length of my pattern is, which in this case is a 4, meaning that every 4th term is going to be the end of my pattern of 4 as well. Okay, so what I need to do is figure out something that's close to 103 that's divisible by 4. All right, well, I know that 100 is divisible by 4, meaning that the 100th term will be a 4. And then from there, what I can do is I can count up to the 101st term, which would be just the beginning of my pattern again, a 1. 102nd would be a 2, and 103 would be a 3. All right, so I know that my 103rd term would just be a 3. Other thing I could do is I go above it. I could also figure out pretty easily that 104, or the 104th term, is divisible by 4, so it's a 4. And then I could count backwards. Either way, I can figure out that that 3 is the 103rd term. Next thing we're going to do is looking at and using inductive reasoning on real-world data. Again, there's going to be a catch to this, a little difference between real-world and math class that we want to point out. So what I have here is a graph that shows the month and number of backpacks sold in that month. So for example, in November, N for November, it looks like there was 11,000 backpacks sold. And in F for February, there's about 9,500 sold. Okay, part A says, what conjecture can you make about backpack sales in May? Well, the pattern it looks like I have is it looks like sales trend in basically a straight line. Meaning that if I want to know how many backpacks were sold in May, I'll follow up from May to my line and then track that over to about, we'll say, 8,000 backpacks. Okay, now here's the difference between real-world data and a pattern in math class. Okay, and B, it asks, what conjecture can you make about backpack sales in June or July? Now the graph I has only shows the backpack sales decreasing, but I know that sometime in the summer backpack sales are going to go back up because of back to school shopping. Okay, this graph doesn't show when that's going to happen. So for that reason, I'm going to say no conclusion. Okay, whoops, got some extra stuff there. In general, for the real world, you only want to make predictions with stuff that's either very close to your data or within your data range. You don't want to project too far out of it, just because, like we said, in math class, those patterns will continue. Real world, they won't necessarily keep on going forever. All right, the last thing we're going to talk about is the idea of a counterexample. Now, a counterexample is an example that shows that a conjecture is incorrect. Okay, so if we want to determine whether or not what we're coming up with, the results we're getting, the conjectures we're making are right or not, one thing we can do is we can see if we can find a counterexample of that conjecture to see if we can prove it's incorrect. All right, so problem 4 says, what is a counterexample for each conjecture? Conjecture we have in part A says, if a month starts with a J, it is a summer month. Okay, why would you make a conjecture like this? Let's say you don't know anything about English. You flip open a calendar in the summer. You say June, it starts with a J, and it's in the summer. Okay, you see July, it starts with a J, it's in the summer as well. And you start to notice a pattern. Okay, so you may make the conjecture, if the name of a month starts with a J, it's in the summer. A counterexample of that conjecture would be January. Okay, because it is a month that starts with a J, but it's not in the summer. Okay, let's look at a few more bad conjectures and find counterexamples to prove them incorrect. B, you can connect any 3 points to form a triangle. Okay, where would this conjecture come from? Let's say I make points 1, 2, 3, and connect them. Hey, there's a triangle. Points 1, 2, 3. Okay, connect them again. Missed, but there's a triangle. We go 1, 2, 3, some closer together points. Looks like I can always make a triangle. Now, a counter to the example of this would be 3 collinear points. I think I need another L. In other words, 3 points that fall on a straight line. Okay, I can't make a triangle out of those because the triangle can't actually open up. It's just a straight line. Okay, now the power of a counterexample is I gave you 3 examples that show the conjecture is true, and all it took was a single counterexample to disprove it. It wouldn't matter if I gave you 300 examples, 3 million good triangles made out of 3 points. Okay, all it takes is one counterexample to show that example is incorrect. All right, let's do a few more of those examples. CS says, when you multiply a number by 2, the product is greater than the original number. So for example, we could say 2 times 3 equals 6. All right, 6 is greater than that original number 3. Or 2 times 14 is equal to 28. Again, 28 is greater than 14. Okay, a counterexample of this could be something like 0, because 2 times 0 is equal to 0. Okay, 0 is not greater than 0, it's equal to 0, so 0 could be a counterexample. All right, or we could pick some negatives. There could be more than one counterexample. 2 times negative 1 is equal to negative 2. All right, negative 2 is not greater than negative 1, it's less than. All right, so negative 1 would be a good counterexample as well. Okay, last one, D, if a flower is red, then it is a rose. Why would you make a conjecture like this? Well, let's say I've seen hundreds of flowers in my life. They're red flowers, and they're always roses. Okay, I could get in the train of thought that all red flowers are roses because that's all I ever see. But a counterexample to that could be another red flower such as a poppy, which is also red, but it's not a rose. Okay, or we could do carnations, or we could do red tulips, basically any red flower that's not a rose. All right, so that's it for our section on inductive reasoning. I want you to start cranking through the homework, start finding some patterns, making some conjectures, and if you get stuck, let us know. We're here to help you out.